Hello everyone, welcome to the second week of the lectures in the course Diffusion in Solids. Last week we went through the introduction to diffusion. I told you some historical developments that happened in the field of diffusion. We also prepared ourselves by revisiting certain mathematical concepts that may be required in the course. Then we also introduced what is the most fundamental part of diffusion as far as solving the mathematical problems or understanding the continuum approach is concerned, that is the Fick's laws. So, we saw Fick's first law, we saw Fick's second law, how they are connected by the equation of continuity. Then we also did what is known as the Laplace transform. That was another important portion which will now help us to understand how to solve, or we will use the Laplace transform rather to solve the various diffusion equations. So, basically in this particular week we will be applying the Laplace transform to Fick's second law, to solving the differential equation, and then take up various cases of the diffusion related problem and solve them. So, let us go ahead. These are the concepts covered today, and these are the keywords. So, before we go to deriving the Laplace transform of Fick's second law, I thought it is also important to visit one more integral rule, which is in addition to what we already covered in our mathematical concepts lecture, which is known as Leibniz integral rule. Although this is useful as such in one step while deriving the Laplace transform of Fick's second law, as a student I was always curious that whether how does that work. So, I will tell you, I thought it may be not a bad idea to have a look at this. So, what it says is that so this is what I already said, that this is a partial differential equation basically. Now, we want to use the Laplace transform to basically transform this equation, which is a partial differential equation, to an ordinary differential equation. So, as I said before we derive that, let us look at an important integral rule which is known as the Leibniz integral rule. Now, what is this integral rule? It is basically concerning the differentiation of an integral. You see that both the important branches of calculus are covered in this rule. So, which is differentiating an integral. So, in its simplest form, there is a more general form of Leibniz integral also available, but I think for our discussion maybe it is okay to use the simpler form, which says that if you want to differentiate an integral which is an integral of a function, let us say f of x t dt, then you can take this derivative inside, and this will be equal to integral a to b dou by dou x of f of x t dt. Now, the actual proof of this is beyond the scope of this particular course, but there are references available on the internet you can look at, or some textbooks on calculus will also give you the proof. In fact, as I told you, in the most general form, even this a and b need not be the function or need not be the constant. It may also be function of x. So, this is a rule again, just to state, understand that d by dx of integral a to b f of x t dt is equal to a to b integral of dou by dou x of f of x t dt. I will show you one example of the application of this integral rule for those who have slightly more inclination towards maths. You will find it interesting. For example, let us say if we want to solve this integral, which is this definite integral, which is t cube minus 1 divided by log t dt from 0 to 1. Now, this integral, if you try to solve without using this integral rule, this is little bit resistant to the standard techniques like partial fractions or integration by parts or substitution, etc. You can give it a try if you find another way of solving this. But I will show you how can we solve this using a Leibniz integral rule. So to do that, what we do usually is we define a function g of x is equal to 0 to 1 t of t to the power x minus 1 divided by ln t dt. Remember, in the original integral you have t cube minus 1, whereas here I am defining a function with g of x, which is t power x minus 1 by ln t into dt. So this x basically when I solve for gx, I just need to evaluate g of 3, which will give me the answer for my original problem. So now once I have defined what is g of x, then I now want to take the derivative of this. So g dash of x is equal to d by dx of this integral. Now if you use the Leibniz integral rule, what I can write is d by dx of 0 to 1 tx minus 1 divided by ln t is equal to 0 to 1 dou by dou x of this particular quantity, which is t to the power x minus 1 by ln t. Now, what is the differentiation of this particular thing? So you will see that this composes of so here ln t is basically not containing any terms of x, so it is like a constant for this differentiation, and the differentiation of t to the power x is nothing but t to the power x log t, and the differentiation of 1 is of course 0. So therefore the g dash of x can be written as 0 to 1 integral t to the power x log t by log t dt, and of course this log t cancels out, and now you have a very simple integral, which is 0 to 1 t to the power x dt, and this we know very well. The integral is t to the power x plus 1 divided by x plus 1. Since here the integration variable is dt, so the x is almost treated like a constant. So now if you put 0 to 1 here, instead of t you will simply get 1 by x plus 1. Now you have g dash is equal to 1 by x plus 1, and we saw that if f of x is or f dash of x is 1 by x plus 1, then f x is, or in this case gx is ln x plus 1 plus constant. Now how do we evaluate this constant? To evaluate this constant, I will just take you back to the definition of the function of gx. So you see that g of x is 0 to 1 t to the power x minus 1 by ln t dt. Now if I put x equal to 0 here, so that is instead of x, if I put 0 here, it becomes 1 minus 1, that is 0. So what we have is actually g of 0 is equal to 0. So g of 0 is equal to 0. So if you put 0 here, that is 0, and here ln 1 is also 0, so that means this constant c is equal to 0. And now you have gx is equal to ln x plus 1. So as I said, once you have the gx to evaluate your original problem, what you need is basically g of 3. So the g of 3 is equal to ln 3 plus 1, which is ln 4, or you can even write it as 2 ln 2. So you see that once if you can utilize the Leibniz integral rule, you can solve it elegantly and arrive at an answer. Without that, the integral is not easy to solve. Of course, not all the integrals can be solved using Leibniz rule, but I encourage you to basically find more examples where this Leibniz integral rule is useful. In fact, just to tell you, the Gaussian integral can be solved using this. Maybe you can give it a try. Now, let us come to transforming the Fick's second law. So, let us resume that. So, you see that you have this equation dou c by dou t is equal to d times dou square c by dou x square. and as I told, this is a partial differential equation. Now, if you rearrange a little bit, what you can write as dou square c by dou x square minus 1 by d dou c by dou t is equal to 0. Now, how do I bring Laplace into here? So, I multiply by the kernel function of the Laplace transform, which is let us say e power minus pt, and then integrating both the sides. Remember this p, or actually when we were talking about Laplace transform, we use the variable s. It does not matter. You can use any variable, any alphabet for the variable. So, once you multiply e power minus pt here and integrate with respect to dt from 0 to infinity, and here also minus 1 by d dou c by dou t into e power minus pt dt, again 0 to infinity equal to 0. Now, we have two integrals to solve. One is here, which is dou square c by dou x square e power minus pt dt, and another is here, which is 1 over d dou c by dou t into e power minus pt dt. Let us see how do we solve them. So, to evaluate the first integral, this is where we use the Leibniz rule. So, you see, we are actually, what we saw in the example in the Leibniz rule, we will be doing a slightly reverse of that. So, you have 0 to infinity dou square c by dou x square e power minus pt dt. Now, I can take this dou square by dou x square out, and it would look something like this. So, dou square by dou x square of this entire integral 0 to infinity c times e power minus pt dt. Remember, just for the brevity, I have written this as c, but in remember that actually it is c x comma t. I will elaborate it a little bit later also, but remember that this is c of x comma t. Now, c into e power minus pt dt. What is this? I think based on the last lecture, you may remember that the way we define the Laplace transform is 0 to infinity integral c into e power minus pt dt, which is the Laplace transform of c. So, we denote it here by c bar. Now, the value of integral therefore becomes dou square c bar by dou x square. So, just to recap here, that we had this integral here. Now, you see one is with x, another is with respect to t. So, now we make use of the Leibniz integral rule and take the derivative outside, and now it becomes the dou square c bar by dou x square. Now, how do I evaluate the second integral? The second integral has both the terms in one variable. So, e power minus pt dou c by dou t times into dt from 0 to infinity. So, now if you use the integration by parts, what you get is 1 over d. So, this is your first function, e power minus pt, and integral of dou c by dou t is nothing but c. I have just written here c of x comma t, and then it is just to put the limits, after putting limits it becomes a little more clear, and the limit are from 0 to infinity, minus the integration 0 to infinity of the derivative of this function. So, the derivative of this function is nothing but minus p into e power minus pt multiplied by c x comma t dt. So, now if you put here infinity instead of t, then you know that e power minus infinity is 0. So, this is 0 here, minus when you put 0 here, this term goes to 1, and here we write it as c of x comma 0. Then the minus minus becomes plus, and you have plus p, which is out of the integral, into e power minus pt c of x comma t dt. By now, you should be able to recognize what is this. This whole integral is nothing but the Laplace transform of c. So, now what it becomes is equal to 1 by d minus c of x comma 0 plus p times c bar. So, Just I will recap once again that we only used simply the integration by parts, and where this was the first function, this was the second function, the integral is simply c of x comma t, and after putting the limits, and here it is the once you differentiate here you get e power minus pt c of x comma t dt, which is nothing but the Laplace transform of c. So almost we are done then, and if you put this values of integral 1 and integral 2 in your equation 1, equation 1 is somewhere here, just for recapping is here, you had integral 1 and integral 2, and therefore what you now get is dou square c bar by dou x square minus 1 by d in bracket minus c of x comma 0 plus p times c bar is equal to 0. And if you rearrange a little bit, what you have is dou square c bar by dou x square minus p c bar by d plus c of x comma 0 is equal to 0. So here you can see basically, so here what you can see actually, so there is a small addition modification I should do here, that so this 1 by d actually comes over the entire integral. So here this bracket is very important, and therefore the here also you will have p c bar by d. Excuse me, it was missed in the original slide, but now we can correct it. And therefore you have 1 by d minus c of x comma 0. Here also you will have p c bar by d, and therefore here also we should write c of x comma 0 by d. So this is basically the Laplace transform of your Fick's second law. What you see is now here, when you have written it in terms of c bar, because you may ask okay, what good it has done, you will appreciate it even more in the next lectures when we actually solve the diffusion equation. But for now I can just tell you that if you observe, now the entire equation is in only terms of one variable, which is x. So now we are utilizing the Laplace transform to transform the partial differential equation to an ordinary differential equation. And here the c of x comma 0 is the initial condition for the diffusion problem. So now in the next lectures we will see how do we apply now this Fick's second law, the transformed Fick's second law, to the various diffusion related problems. So thank you.